Hello, am I audible? Hello, everyone.
Yes, sir.
Okay, so I'll wait for 5 more minutes and then I will start.
Sir?
Yes, hello. I'll wait for 2 3 minutes, then I can start because some people might join also.
Okay, sir. Okay, sir.
So I will actually couldn't take the last two classes because of some other assignments. So I will upload the videos very soon in the YouTube channel. Okay, then probably you guys can find it in the link. From onwards, I
Okay,
will
sir.
take, yeah, from onwards, I would regularly take the classes and please follow it. Yeah.
Yes, sure, sir.
So, which portion currently Digvijay sir is teaching you? Can any of you like mention that? Like, mostly the PN junction diet has been started, right, in the class? Okay, some of you are from NPTL, I think, and some of you are from the college student, I think, from Bolpur College. So, I think. Okay, I can start now. So I will share my screen. Is my screen visible?
Yes, sir. It is visible.
Okay, fine, fine. So I can start now. I think most of the people, or less few people, are still joining. Okay, I can maybe stop and keep on adding. So yeah, in the last class, basically, I'll just quickly revise few of the topics. So these are the things that has been I covered mostly with some question answer. So I taught you the basics of semiconductor physics. Please unmute yourself if anyone some other sounds are coming. Yeah, one second. Let me see who is not muted. Okay, I have muted this person. Please make sure that all of you are muted unless you want to ask some question. Otherwise, it can create some problem for other students. Yeah. So these are the topics that has been already taught. So I covered the basics of semiconductor physics, the valence band and conduction band, and the expression of the Fermi energy, and the carrier concentration expression for both the intrinsic and extrinsic semiconductor, and particularly for its direct and indirect bandgap semiconductor. So today I will also teach you a couple of things from semiconductor physics itself. Then I'll slowly move towards the PN junction. Okay, and there are few topics that actually I couldn't cover in the last class. Those are actually important. So one of which is Einstein equation. So before I go there, I would like to derive some of the expression, and that expressions are very important. So probably, yeah, I can start with that. So the drift current density. So uh, yes. So in any point of time, my screen gets frozen or something, then please immediately tell me. Yeah, I hope it is visible. So the drift current density due to electrons in the semiconductors, let's say this is Jn1, J equals to NeV. This I already derived all these things in my last class. I will also share the note shortly. This is the drift, Vdn is the drift velocity, and you can also write in terms of the mobility. Here your mobility of the electrons, mu1 is defined in that way. Yeah, as this is another expression. This is the applied electric field. Okay, and similarly for the holes, you can write in terms of Jp1. Similarly, it will be Ep mu p E. So this is how the total drift current in the semiconductor, which is Jd mu p E. Got it? Then I will discuss the diffusion current. Yeah. With some expressions. So how the electron and hole diffusion occurs generally in a system. So suppose you have a semiconductor. So let's say something like, so here the density is 0. The diffusion is occurring along the x-axis. Okay. So this you can consider, this is one dimensional. That is why it's dp dx. This is the drift current density. Maybe you can write also like, yeah. So suppose in semiconductors there is a your concentration gradient of the holes. So these concepts are very important actually. Concentration gradient of holes, that is equals to dp dx. Okay, and basically this whole concentration in decreases with the increase of distance x. That is why it will when we write it will minus sign will come. So the diffusion current density is basically proportional to this concentration gradient, and which is given by jp2, which is minus d. Why minus? Because as I already mentioned, along the x-axis the concentration is decreasing, so that is why dp dx, this first derivative has a minus sign occurring here. Okay, and here dp is basically called diffusion coefficient. Okay, please get familiar, be familiar with this terminologies, because in exams people like there you might find a lot of question related to this in any kind of competitive exam also. uh, or this is the diffusion constant for the holes. Now basically we can so dpdx is negative, that is why we have put the sign over there. Now similarly, the diffusion electron current density is Jn2 Now, for a semiconductor containing both the free electrons and the holes, the resultant diffusion current density will be is equals to defined as JD dN, and there will be a minus sign, I already told you, then dpdx. Maybe we are defining this first expression as a equation number 1 for today, or maybe we can, okay, I think we can, this is 1, let's say this is I'm putting as 1, because later on when I'll do like some problem solution, this will be required. So this I'm giving as, then okay, this is 2, and then this will eventually become 3. This is 3, equation number 3. So this is the diffusion current. Okay, but already in semiconductor I just told you about the drift current as well, right? So that is a different thing which I already told you. There's a both combination which is coming from the drift and diffusion. So it will be drift, the total current is the combination of drift and diffusion of the charge carrier, like electrons and holes. So the total current density J in a semiconductor is sum of drift, which I am defining as maybe small d, let's say, and the capital D is basically diffusion. Okay, so this thing I already just wrote it before within terms of the electric fields and mobility, and now the diffusion come. Okay, this we can put as equation number 4. Now I'll come to something. So this is done. Something is called Einstein relationship. That is an important thing. Called Einstein relationship for semiconductors. Yeah. So
Hello, sir.
yes.
Sir, why the dp is negative and dn is positive?
Because of the nature of the charge carrier, electron is always negatively charged and holes are by definition positively charged. So their direction is different. So at results, it will, for the diffusion case, it is negative when it is occurring. But for the total transport which is coming, it's a combination of both the charges. That is why we are considering the modulus. But for the diffusion, it's a conventional thing. We are taking a, because it's a flow in a particular direction, right? So if you go back to this particular thing, yeah, here we are considering for the holes, it's opposite to the, I mean, it's a definition, right? So that is why net conduction diffusion current is actually the subtraction of both the terms, like the electron and the hole. But for the total drift current, we don't consider this. I mean, you can later on put it, but you will find it to be the same. Yeah. Just a
Okay, sir.
definition. I mean,
So,
later on, yeah, yeah.
yeah. So, what is the direction of drift and diffusion of electrons and holes?
So that is what I'm saying. Type of charge carrier, right? But when in the case of recombination, what I told you, when electron and hole recombine, they can emit a photon. That's a different process altogether. But if you consider there is a charge moving, let's say from this side to this side, here to here, then always electron leaves a vacancy here. So the direction of the holes basically will be opposite to this, right? Because there will be a vacancy, and that vacancy is basically defined as a hole concentration. Okay, because that technically is that local, that thing is positively charged now, because this electron uh, already left that place and moving to the other side. So that is why there is a deficiency of the negative charge. So we call it as a positive charge, which is by definition we call as hole. So it's the opposite to that. Understand?
Yes, sir.
Okay.
So, during
So
the
it's a
formation of
convention. Yeah.
p-n junction, there is hole concentration in p type and electron
Yeah,
concentration
I will
in.
come to that. All these things. It's I as I told you. So PN junction,
Okay,
I have
sir.
not started yet. So I will
Yeah, yeah.
come to that. Then probably you can discuss all these things. Yeah.
Okay, sir.
Today only I will try to cover. If not, then probably in the next class. Fine.
Okay,
Okay.
sir.
Yeah. Yeah. So I was talking about the Einstein relationship. So let's say in equilibrium situation, particularly as just you pointed out, there could be a situation when we get a condition that electrons are whole currents are completely becoming equal. Okay, let's say not going into the directional method, but if we talk that, if we sometimes what happens, like in the case of, you have guys all the familiar with the Newton's laws of motion, right? So for for each action there will be a equal and opposite reaction, right? So the force direction could be different, but the magnitudes are same. So if we consider that for the time being, let's say the same thing in the classical mechanics you guys have already learned. So in equilibrium conditions, the total net force is always zero, right? So in the same analogy, if we think there is an equilibrium situation in the semiconductor physics also, where these two currents, which basically coming from the hole component and the electron component, is becoming equal. Okay, then what will be the situation from the drift and the diffusion term? Then simply for the time being, if we consider the mod of this thing too, okay, we're not considering the total direction, then it will eventually become zero, right? Well, let's say this drift and diffusion under the equilibrium, then these are equal. So I'm particularly talking about this thing. Then for force on the force on the electrons that is contained in unit volume due to the electric field. This is the electric field. Okay, this is also vector, but here, as I am mentioning, the magnitude is same. That is why I put in a scalar form. Okay, so it will be F equals to the force basically unit volume is in E, right? Because it's directly from the Coulomb's law. And d and dx. So basically, from the kinetic theory, we can also derive an analogous expression for the F, that assuming the electrons to from a classical electronic gas. Okay, so the expression for the pressure then becomes P here. P is basically the pressure. P equals to, it's very simple. It's in kT, right? And the force per unit volume is basically, it's a gradient of the pressure. That's how we defining the force, right? In classical mechanics, kT d and dx, because there is a gradient of the density. There is a diffusion that is occurring, right? So now we are comparing this equation. Let's say I'm putting this equation name as, already I put a 4, so let's call it as a 5 maybe. Yeah, this is 5, and this we can write as 6. So now we are comparing this to equation 5 and 6. You will eventually get this thing, right? So this for the electrons. So please remember this expression. This is very important actually. So this is only valid under equilibrium. Okay, so this is for electrons. Maybe we can name it as equation number 8, and similarly for holes it will become dp mu p kt by e, which is equation number 8. So this equation basically, particularly these two equations, equation 7 and 8, are known as Einstein relationship. Einstein relationship between mobility and diffusion constant. Please uh, remember this formula. Okay, done. And there is another expression called the diffusion length, or the, I can just quickly also show you, but you can also remember, I'm not like going to derive this thing. It will take time. So for any kind of semiconducting bar, let's say this you can standard find it. I mean any kind of standard textbook. The diffuse, there is a term called diffusion length. You can try finding this thing by yourself. If you can't, I can probably show you in the next class. This is the tau. This is the tau is the time, and this is the diffusion constant. And this is the length. With this, we can put as equation number 9. Yeah, this is called the diffusion length for the electrons. Now there is something which is also important if we talk about the Hall effect in a semiconductor that I have not discussed actually in the last class. So you might expect some of the question from that side also. I think you guys are familiar with the Hall effect. So if we apply a magnetic field in plane, then how the charge carrier basically, I mean, depending on charge carriers are confined in a plane, and if you're applying a magnetic field, what will be the Hall resistance and Hall coefficient is a simple thing. So the Hall coefficient is basically, so for particularly for semiconductor context, it is very important because we have two type of charge carrier that are present here. So we need to know this all these things. So the standard Hall coefficient is basically which is developed here is 1 by EP. Okay. So for N type of semiconductor, let's say I'm also designing the circuit for this. You're applying, sorry, maybe I can change the color. Magnetic field is perpendicular on z direction. The electric field is basically V cross B. Maybe you can define the thickness as D. This is for the P type semiconductor. And if we do the same thing for N type semiconductor, this is how it will look like. Sorry. This is for the n-type. So for the n-type semiconductor, the majority carriers are negatively charged. As for along the x direction, electron. So for the current density along the x direction, electron moves along the x direction. The magnetic field basically try to deflect the electron towards minus y direction, right? So the Hall voltage in this case Hall field, or you can also say Hall voltage also, is developed. This is very crucial. Developed in a direction opposite to the p-type semiconductor. So the Hall coefficient will be given by, there will be negative sign for electron, right? Now the Hall coefficient including the both electron and holes may be derived as follows, that I'll do this here. The current density along x direction due to electrons no minus x direction with drift velocity because it's electron, right? So your drift current minus E Vxc. Okay. So this we can put a equation number also. Let me check. This is 9 and this let me put as 10. Then this will become 11. Okay. Mu is basically your electron mobility. Ex is basically your applied electric field along x direction. This is a very straightforward. So the average force on an electron due to the applied magnetic field applied B field in short okay, it's Q times V cross B. Okay, Lorentz law is basically, you know this, so it's a cross product of the V cross B and times the charge. Here charge of the electron is minus E, it's negatively charged. Okay, so coming from the Lorentz law, for Lorentz force, sorry. Okay, sorry. If we substitute all the values, You can check this. Now if be the developed Hall field along y direction, the net force on an electron along y direction is basically then V cross V, the electric field plus the magnetic field force term. You just have to substitute from the earlier equation. That's it. Then the associated deflected current density density is given by this mu, sorry. Similarly for holes, a positive sign, positive charge, and moving along x direction. I'll come to the some of the question answer after this. So now the total current densities, which is Jx equals to Jxc, Jxh, So now in equilibrium condition, there is no current flow generally along y direction. So simply you can consider Jy to be 0 and corresponding EH. If you simplify, you will find the EH will be turn out to be like this. So by definition, the Hall coefficient now becomes RH equals to EH by Pjx P p square minus n un square square. Okay. Now there are certain cases like if we talk about the intrinsic semiconductor. The intrinsic semiconductor is basically, I already told you in earlier class, it's N equals to P equals to Ni, right? This is applicable for any intrinsic semiconductor. So we'll apply that. So RH is eventually for intrinsic cases will become. So this is a very important expression actually. You might expect some questions from based on this equation. So if you remember this thing, the idea and the particularly this, you will be able to solve a lot of questions which will be coming for the exams. So now you can number this equation. Let me check. Already we this is 11 has been given. Okay, let me write it 12. Okay, this is a very important one. Okay. Now, so particularly if I do it more generalization, sorry, more specific case like this, I told you for intrinsic. Now let's say I have N-type semiconductor. Okay, so what is the criteria for N-type semiconductor? So it's mainly N dope, like electron dope. N is greater than P. What will be the what will be the your Hall coefficient is basically this, right? So you can check this thing. I mean, N is greater than P. So this will eventually become something like this. And for P-type semiconductor, this is ulta, which is P is basically greater than N, not the N1. Then also RH becomes positive, like EP. Okay, fine. So this is done. So this actually was the important expression. I thought probably you guys should know these things. This probably I can know 13 and 14 equation number. Yes. Okay. People are still joining actually, but it's better if you guys join by sharp 3 because already half of the class is done. Okay, now I'll do some like as for this course particularly, I'm not directly allowed to discuss the assignments, but some of the model questions answer I can just discuss with you guys. So there is no previous year's concept for this particular assignment. So I had come out with some questions that I will solve live. Probably you guys can follow it. So just I to so if you remember all these things, if I just 2 minutes. Yeah, so there is a problem, question and answer. Then I will come to the PN junction. So suppose the basically question is the Hall effect is used to determine the mobility of the holes in a p-type silicon bar. Okay, the measured values of current and Hall voltage, the current values are given. So I'll just write down the important thing parameter that which are given, because after all you have to use the equation and you have to solve, so there is no need to write the full question. So the current, the measured values of the current is 10 micrometer ampere, which is given in the question, and the Hall voltage basically is 50 millivolt. Okay. Now we are assuming the resistivity of the bar. The silicon bar has been used here. The resistivity of the bar is also given in the question. Maybe you can write rho, not H, but maybe simply rho. Rho is stands for the resistivity, which is 2 times 10 power 3 ohm meter. Okay, for two-dimensional case. And the magnetic field is basically 0.1 Tesla. Okay, and the thickness and the width of the bar are respectively, let's say d is the thickness, and also uh, width, both are same, which is given as 3 millimeter. So you are asked to find what will be the corresponding mobility for the p component, okay, which is mu p. So now you already know from the what will be the Hall coefficient. Hall voltage is already given, which is IB, right? You just have to use this one to solve this. Everything is given. Basically, the conductivity is 1 over resistivity. So 2 times 10 power 3. So it's basically sigma equals to any mu. And from that also the connecting Hall voltage expression is this. And this is in terms of meter square per volt second. Okay, in SI unit you have to write it. So you can calculate by yourself. It will eventually become 0.075 meter square per volt second. Okay. Now I'll discuss one thing from the your one sec. Let me change the color. There's a question is so that the fractional charge in the conductivity of an intrinsic semiconductor is given by delta sigma by sigma. Basically, using the above expression, above results show that the conductivity of silicon at room temperature increases approximately by 8% per degree rise in the temperature. Okay, so that you have to show. Fine. So there are other given things also there. Which is the intrinsic band gap of the semiconductor, which is 1.2 electron volt, and KT is this If you convert this to electron volt, you will get something like 0.026 at room temperature. Just put the Boltzmann constant and you will get that. Sorry. So we have for the intrinsic semiconductor. This I already told in the last classes. Okay, I'm not going to show this thing. You already, if you find the whatever equation I have written earlier, it's coming from that. And sigma equals to any mu, right? Maybe in I can take outside the bracket. So, but the mobilities are not same for the p and uh, electron and hole doped charge carrier, so it is outside ni. And now if we just take the log, okay, on both the sides, so dni. So yeah, from this expression you have to plug it in here, so you will get 3 by 2, whereas we are taking log dt by t plus eg naught 2 kt square dt dt by t. So now the silicon is at the room temperature, and your eg is, that is also given, eg naught, which is 1.2 electron volt, and kt is 0.026 electron volt, and temperature is room temperature 300 Kelvin. Okay, so now therefore the dt is 1 Kelvin. For dt, okay, so this is for dt 1 Kelvin, the d sigma by sigma, how much increase is expected. We have to show it that it is whether having 8% or not. So let's see, let's put the values. 0.26. If you check it will become close to 0.08 in fraction. So yeah, this is coming to be 8%, so it is fine. Now another last problem from this thing section, then I'll come to p-n junction. So in n-type silicon at room temperature, find the donor concentration, which is nd, for which the Fermi level coincides with the age of the conduction band. Okay, it's a very easy one. So assume that the effective mass of the electron is equals to the true mass. So what is the expression we know? So I already defined in the last classes how the Fermi energy is basically related to the age of the conduction band and the age of the valence band, how it is related to the your donor concentration or carrier concentration, right? So this is how it has been defined, where this also I have shown you earlier, but for the time being I'm just writing 2 pi me star kt. You guys have to remember all this expression. This is a very important. So 3 by 2. Okay. So now already the question, if it's saying that EF equals to, it is exactly the Fermi energy is aligning with the age of the conduction band. So this is given. Okay. Right. So basically this term is 0 then, right? It will, sorry, this will be ln of, sorry, this is ln of, not, I forgot it, just one sec. This, there is a log ln of this thing, sorry, ln of nc by nd. Okay, so this term eventually becomes 0, ln of NC by ND. So basically it has to NC equals to ND, right? So now the donor concentration ND is equals to, just plug in all the value whatever is given. Okay, and you have to use this one. This will directly come here. You plug in the values, you will get something like 2.5 10 power 25 per meter square. Sorry, per meter cube. It's in 3D. Okay, you guys solve it by yourself and check how it is coming. Now I'll come to the PN junction portion. This is basically the semiconductor diodes and their application I'll be discussing about. Then I will probably discuss some of the detailed, maybe question answer will come in the next class, because it will take today's class at least, because I have 1 hour left. So mainly I will discuss some of the important concepts today, and then the solution problem answer maybe will resume from the next class. If you guys have any question, you can ask also. Okay, this is also, I think, the class. This is very standard. First, I will start with the schematic. So, how the PN junction is defined mainly. So now, basically, we are sandwiching this two highly electron and hold-off side, and there is an intermediate section which is called the PN junction. It's exactly lie at the center of this of the semiconductor. So one side maybe so P dot, another side defining as N. Okay, electron and holes. This does the convention. So you will find one side some majority charge carrier. Okay, it's mainly electrons on this side for P type, and there will find some minority like uh, charge carrier in between, but this is a minority. Okay, not the majority. Okay. So acceptor ion. This is the junction that is getting formed in between this N and P doped semiconductor. But here this is ulta, the majority donor and positive. This is the junction. Okay, this is how we define it. Now we are considering the PN junction, whose P side is also generally doped uniformly with a concentration with, let's say we are defining at Na, and the N side probably we are doping with a concentration. We are not keeping it equal intentionally so that we can derive a general expression. Okay, so this side is Nd. So let the junction be abrupt, and that is there is an abrupt change in the P type impurity to N type impurity, and we'll also show how the variation in the space charge density occurring here. with the distance from the junction basically. Okay, so this is the draw a vertical line. So this probably I will do this once I derive the expression. I'm keeping it for the time being blank. Once I derive, then probably I will come back here. Okay, so now everything is black. So in any kind of like open, so because of this phase charge, an intrinsic potential barrier that generally develops across the junction. So the potential barrier, because of this change in, because of the difference in the charge on both the sides, the potential barrier which we are defining as VB across the junction, okay, which is getting developed across the junction. So in an open circuited PN junction, net electron and hole current density must be zero separately, right? It's completely separated then, open circuit, because the electron is not flowing, and so zero separately. So considering only holes, the JP, which I, this again coming from the drift and diffusion that I just today explained you. There's a two component which is coming from the drift and another is the diffusion current of the charge carrier. If you go back to the earlier expression, you will find this dp dx is also zero, right? Where E is basically the built-in electric field and the other symbols basically tells their usual meaning. So also use the Einstein relation now. So that is why it's very interconnected. So you have to understand why I today, before coming to the PN junction, I discussed all this drift diffusion and the Einstein relation, because these are very interconnected concepts. So until and unless those are clear, you won't be able to move forward with this idea of the PN junction and all. So yeah, that is why it has been discussed earlier, so that we get the clarity. So now we'll use the Einstein expression. So I'm deriving this thing because so that the fundamental concepts are very much clear from the like schematic level, how the equations are propagating and we getting all this expression which eventually you guys will be using for solving the questions. So that is why these are very important. So using the Einstein relation, which I already shown you guys earlier, it's simply this. Okay, now from let me check how many people have joined so far. They're still joining. Okay, fine. Yeah, done. So basically you take this expression, plug it in here, and then further you get uh, dp by p, dp by p, e by kt, e dx. Okay. So now the potential variation is obtained by using the relation E equals to minus dv dx. Okay, that I forgot to mention, so remember this thing. Okay, now integrating from, so we'll be deriving a very important expression. That is why I'm starting from the scratch. Integrating from p region to n region minus xp to plus xn, we get the potential rise from p to n region, right? Respectively. So pn will become basically, one sec. So already you have this equation. You have to just integrate on both the sides. It would, if I take from here, it's very easy actually. It will give me some form of ln pn by pp, then minus e by kt vn plus pp minus e by kt vb. Okay, here vb is the potential drop across the barrier that I told. It is bn plus vp is the potential barrier. And pp and pn is the concentration I already told you on the p and n region respectively. Okay, so if further integrate this thing, what you will get is, sorry, some gone up by mistake. Yeah, so you will get something like, you just have to integrate. Okay, vb by kt. Okay, now at moderate temperatures typically all the impurity atoms are ionized, and the equilibrium concentration of the holes in the p side is, let's say, pp pp naught equals to n. It's basically coming from the acceptor ions, right, which I told you here. It's basically na on the p side, the left side of the pn junction. And that true also for the inside, which is pn. Sorry, no, I cannot write p here. It will be n for the electrons, not nd. It's a donor type. This is acceptor, this is donor. Okay, so now the concentration of the minority holes in the inside is given by the mass action law, right? So from mass action, that also I discussed in the last class. What is mass action law? So if you simply use this, you can determine the concentration of the minority holes. Consent, I'll rewrite again so that, okay, just inside is given by using mass action law, which is Pn. This for the intrinsic semiconductor Ni square and then Nn. Okay, so Ni square by Nd. Therefore, from this above expression, this one, we can easily write the potential barrier This is a very like most important part why I was deriving, just to get the potential barrier with. If you use this two above expression, you will get something like this. NAND by NI square. Please remember this expression. It's very important. This is the potential barrier across the junction. Okay. Generally, you can check this thing for VB for. I will write it also. You can remember the VB, the value of the silicon and germanium of VB for germanium equals to 0.5 volt, and for silicon 0.7 volt. Okay, done. Okay, next I think I will derive the depletion region ka width. The PN junction, which is got developed at the center of the two semiconductor. This is also important. The width of the depletion region. Yeah. So to find an expression for the width of the depletion region, so basically from the Poisson's equation in one dimension, we need this help of Poisson's to derive this thing. The Poisson equation in 1D channel, one dimensional, as the acceptor density for, let's say, x less than 0. Okay, so probably I will come back to the schematic, and this you can write. I mean, as we have to define the width of the depletion region. So I will come to how this all potential barrier, all this potential electric field looks like. Once the derivation is complete, I will come back and show you one by one. So this is maybe along the x-axis you can think, and this is x equals to 0. Okay, so we have two conditions here. One is for x greater less than 0, one is for x greater than 0. Okay, so this on the left side. So that is why I write NA. Now what happened, the Poisson equation will change also, because there is donut type of charge carrier. So that is why it is minus END for x greater than 0. Okay, where epsilon is the absolute permittivity of the medium. Now if we basically integrate these two equation, what we'll get? So what number I will give for this equations, I have to check. Earlier we ended up with equation number, I think, okay, 13 14. That is the last equation number I wrote. So 30 14. After that I have not numbered any of the equations. So okay, we can define as maybe 15 16, let's say. So if we integrate these two equations, we get something like, to integrate individually, integrating, we obtain dv dx ena x plus c1. One constant will be there because the limit is not provided, it is ill-defined. So e n d epsilon x plus c2. Okay, to find the constant of the integration, apply the boundary condition. Okay, so dv dx is basically your 0 at x equals to minus xp and x equals to xn. So c1 also, you obtained the value xp. Okay, so from equation, this to above equation, we finally get xn minus x. Good. To get the final potential form as a function of x, you have to integrate further. Okay, this is still in the first order. That was the second order, d2v dx square. We integrated, we get the first order dv dx. Again we get, so that we get the actual v as a function of x. Integrating further, we get again another constant will come. This we don't have the limit, and put the boundary condition and we can solve. C4. Again use the boundary condition. So vp equals to minus, v equals to minus vp at x equals to minus xp, and v equals to vn at x equals to xn. Thus we get, v equals to minus vp plus ena 2 epsilon naught xp plus x square, and v equals to vn minus e nd 2 epsilon naught xn minus x square. Done. Now at x equals to 0, both the solutions should give should give the same value of dvdx and v, right? So now we basically equate this to expression of dvdx at x equals to 0. It's a something called continuity across x equals to 0 point, right? And hence we get, if you can check that, NAXP in dxn. Okay, this is basically the charge neutrality condition, you can say. Therefore xp equals to xp plus xn equals to nd na plus nd, and xn equals to xn by now equating the values of v at x equals to 0, and we are using the above this expression. We get, hence we get vp Now finally we can estimate the width of the depletion layer, the width of the, because we already got the xp plus xn, because the contribution comes from both the sides, right? In order to calculate the depletion width. Or you can also write w equals to ln of nd to the power half. Okay. Therefore, this value of W depends on the concentration of the impurity atoms on both the sides of p-n junction, right? So typically, the order will be of the order of micrometer, like zero point 0.5, zero point 0.6 micrometer. So, yeah. So the depletion region generally decreases with the increase of the doping concentration. That is very much clear, right? So as we increase the concentration, increase the concentration of the depletion region. So sorry, the doping concentration. So eventually the W will, yeah, get smaller. So I can probably draw this schematic quickly. So where I told you that once I derive, I can come back here. So you can understand this. One sec. Yes. So okay, maybe I just, yeah, this portion. I mean, this kind of diagram you can expect actually in competitive exam. What will be the potential corresponding potential? Sorry. Hmm. So if I talk about the variation of the space charge density, so this is a positive side, right? And so this will be, maybe let me change the color. It will be visible more. So something like this, positive on this side. And then on the negative side we have like something like this. This is the xv, this is the xn, this is the distance we are talking about, the distance from the junction, distance from the junction. Junction means x equals to 0, from the junction. Okay, so this is the space charge density. I'm defining like as rho. Now the potential, if we try to look how it behaves, so something like this. You can also check from the equation, right? This is how it is changing. So positive negative, this is the junction, this is the maximum at x equals to xn or x equals to xp. This will be minus bp at x equals to minus xp, and this is at x equals to xn. Okay, and if you estimate the electric field, generally you will be asked to find out this, what will be the, for a given potential, what will be the, I mean, E is basically your dvdx, right? So to define how the electric field will look like. So this is how your electric field will look like. So I think I will end today's class here. Probably then from the next class I will start. I will also start the diode portion from the next class. Then probably the probable question answer I can discuss. Okay. So if there are any question you can ask, or maybe we'll meet next week. Yeah, I will upload all this thing. Actually, I forgot. Last two classes were missed, so probably I will upload. You will find in that link that the remaining two classes which were not done. So I will upload shortly. Okay. Okay. So okay, fine. If there is no other questions, we can meet next week, Sunday at 3 p.m. same time. Okay. Bye. Guys, please exit from the meeting because otherwise I cannot save uh, the recording is still going on because few people are there. Guys, can you please exit? Or maybe just the person is not there, but the Teams is open. I don't know what's going on. Hello. Yeah, hello. Just unmute. Guys, are you there or just exit from the chat because the recording will not get saved otherwise. People are coming.